All right, so let's get going. Um, we started a new unit yesterday on this hill climbing search stuff. Optimize this a little bit. Okay. All right, let me just remind you what the general algorithm is that we presented so far. Maybe Zoom will get around to letting us see the whole screen. Maybe not. All right. Okay, so this is as you recall, hill climbing is takes a state and tries to improve it again and again and again, and it has discrete and continuous variance. By continuous, we mean when you're optimizing something that has floating point numbers and close enough to continuous for us. Wow. All right. Yeah, so this is the algorithm. You start from your state. You look at all possible neighbor states. Okay, I call those tweaks, right? They're generally pretty close to the state that you're actually in. Okay, and the assumption for hill climbing is that you have a quality function, and your goal is to improve, get a state that's going to be better, with regard to that quality function, period. You're not expecting the absolute best. If you get that, you're very lucky. Okay. And then if we see that we're not doing any better, then we stop. Okay. Look at all the neighbor states and they're just as bad as we are, or maybe worse. Then we'll just stay where we are and say halt. Okay. Otherwise, we take the best one of the neighbors to be the new current state and repeat. Okay. So I think that's pretty obvious, pretty obviously sensible. We went through this example yesterday. You could start from the starting point 3 and you can go and hill climb looking at neighbors, right? And you'll realize that, yeah, you don't get to the absolute best. Okay. And this problem has a name, which we talked about, the problem of local maxima, which there is no solution exists for this problem. We just cope with it various ways. And in particular, by just restarting, if we are lucky enough to be able to draw a random state, okay, and usually we can create at least one state. But what would be nice is to have like a uniform distribution over all states. You can't always expect that. Okay, but if you can, if you do have a non-trivial distribution over states, then you can just restart the process from a new state and hope that, if you end up on the foothills of Mount Everest, right? Speaking of literal hill climbing on the globe, then you'll be lucky and you'll get to the top of Everest, maybe. Okay. And otherwise, you probably won't, but at least this gives you some hope. If you have more computation time, how should you use it? Well, this is an obvious way to do it. Okay. Now, there are variants of this technique that incorporate uphill steps, which we'll talk about, but not in super great detail. But there are some important things that you should know about that. Okay. Let's consider something a little more real than the one-dimensional problem on the slide before. Let's consider solving 8 queens. So that's a non-trivial problem. Tried to solve it and didn't have too much luck as a class. Okay. So what we're going to do is so for 8 queens. So think about it. So to generate a state. So here we're going to have all 8 queens on the board. We're not going to try to do things incrementally because that's not the hill climbing way. You take your best stab at the solution and you try to improve it. So we'll put all 8 queens on the board and we'll call that the current state. And it's obvious this is one where can we generate a random configuration of queens on the board? Sure, it's super easy. Okay, just make sure you don't put 2 on the same square. That's pretty much the only way you can go wrong. Okay. And then we need to define, if we're going to do hill climbing, we have to have a scoring function, a quality function. So what we can do is just count the number of queen pairs that are attacking each other, right? And multiply that by -1 so that positive means better, right? And that could be our quality function. So a true solution to 8 queens will have what quality? 0. 0. That would be the absolute best. Otherwise, quality is negative. Okay, then that's totally fine. Nothing Nothing weird about a negative quality number for a hill climbing search. Now, the last thing we need to do to be ready to actually try to tackle this is to say, what tweaks are you going to allow? Okay. And what I'm allowing is picking up one queen, and moving it to an available position on the board. It says new position, but I looked at the code that I wrote, and it's just a position. Okay, so how many tweaks is that? How many tweaks have to be looked at every time we do one pass through the hill climbing algorithm? 8, because 8 queens? Okay, well, that's part of it. But let's say I grab queen number 2, where does it go? Right? To generate a state, I need more than that. Okay. How many locations are there for queen number 2 on the board?
Is it what's set? You could eliminate that by just removing the current attack space. You move into it.
Well, okay, you're trying to get too sophisticated, so we're not going to go there. But there's 64 squares on a chessboard. 7 of them are occupied. So, there you go. So 64 minus 7, that's what? 57? 57 times 8 queens, because we can move any one of them. So that's, or less than 500 maybe, but 500-ish tweaks. Okay, now that may seem like a lot, but of course for a computer, but just 500 options, that's easy. Okay, and that's in our inner loop. It's going to have to do that again and again and again. Okay, now, good. Link here, so you can take a look. It's not a graphics extravaganza, but should teach us something here, I hope, if it opens. Lovely. Okay, here we go. All right, so it's open console. So let's open the console here. Okay, so this is one run is complete. Let me scroll up to the top. Okay, so what it's done is, yeah, what it's done is it randomly placed 8 queens on the board. Those look random to me. I mean, in other words, terrible, right? And you see the score down here, 11 pairs of queens attacking each other. Okay, and then we ought to be able to look and compare the boards. What's the change between the two? I see a new one popping up here. I guess it's this one, right? And then all the other ones should be in an identical configuration. Is that what you guys see? Okay. All right. And already just doing that, moving that queen, improves our score to -6. So we like eliminated half of the badness. So that's pretty good work for one move of a queen. All right. And then after one more move, we're down to -3. And then we're down to -2. And then we're down to -2. What happened? Current solution is Gable, which we call a local maximum. Yeah, this is a local maximum. It claims. So you can verify, right, by looking to see, is there any queen, just by moving one queen, where you could improve, at least get to maybe -1, if not to an actual solution. And presumably, if you look at this and spend all day on it, it won't matter, because you realize that there is no such move of any one queen, right? That's the nature of a local maximum. We improved greatly from -11. That's the good news. And the bad news is that, well, actually, if we really only want scores of 0, we didn't get there. Okay. And the main tool I offered you against this problem is what? Randomization, random what? Random restart, particular randomization. So particular kind of randomization, and we'll talk about other kinds of randomization before we're done. Okay, so you just restart like that. Okay, there we go. Hopefully you see this is new. It's kind of similar deal, but not exactly, right? Because it has a queen in the top row. And the first, it gets to the same -2. All right, great. Try again. Here we go. Okay, here we go. We got to score of 0, and of course it doesn't know 0 is the maximum, so it tries to improve it even more by looking at all the tweaks. Okay, but there we go. A solution to 8 queens, which, as you know, is not trivial. Andy,
it might be a different algorithm, not climbing, but do you guys ever apply
highest beam out to, do we ever apply a partial restart, so to do the metaphor of the hills and stuff?
Yes, that is a thing. We'll talk about that. Genetic algorithms do something like that. We'll take a look. In my mind, they do. Well, we'll see. We'll see if you're satisfied. That's a connection I would make. Okay, so you can kind of see it's kind of fun to play with this. I mean, all the work's been done for you. It's like, okay, so we ran 3 runs. One got to a solution. Okay, we know solutions are not easy to get to. That's actually really not too bad, especially in terms of the amount of computation we used, which was pretty minimal. And you could just sit and keep playing. There's a fail down with that score of -1, -1, -1. Okay, my stats are going down here. My stats are going, okay, here's another solution. Okay, all right. So you can solve stuff with hill climbing, and people use hill climbing for all kinds of stuff. Okay. And of course, the whole reason we're doing this is because you can't really understand how neural networks are trained unless you understand hill climbing, but that is in the continuous domain. So stay tuned. All right. Any questions on this? All right. All right. All right. So now let's talk about noise. So there are 2 famous algorithms that you should know about, even with a very brief treatment. This is hill climbing. One was called simulated annealing, which was invented back in the 80s. Got you at the net at the time. Got into neural networks after that. It was invented at IBM for the problem of laying out circuit boards. Right? So imagine if an engineer says, okay, these are the components that need to go on your circuit board, and here is how all the pins are created. Would you please lay this out for me so we can actually manufacture this thing? And oh, by the way, we'd like the thing to be as small as possible. And oh, by the way, we'd like the total wiring distance to be as small as possible because you lose, you gain heat, right? Wires radiate heat, even tiny ones on a circuit board. So to keep heat low, we'd like to make the whole thing small. To keep manufacturing costs low, we'd like the whole device to be small, yada, yada. Okay? This was a hard problem. It was done pretty much by hand in early days. And Scott Kirkpatrick, the guy who invented this, figured out that, okay, this was a case where some noise could do a world of good. This is noisy hill climbing. Okay, now, Scott being a physicist, he used this thing called the Boltzmann distribution, which you'd have to, if you're a mechanical engineer or a physicist, you should recognize that. So it has to do with, if you look at the distribution of energies, bare molecules in this room, it follows a Boltzmann distribution, right? And the average goes by the temperature, but there's plenty of molecules that are lazy and not moving very much below the average, and then there'll be a few that are zipping around incredibly fast. Okay? That's a Boltzmann distribution. I'll show you that distribution because it's not just a fun detail footnote from physics. It comes up a lot in modern data. Okay, and I don't think there's any magic to it, but it's because it was there. It just ends up being pressed into service again and again and again and again. And I'll show you that in a minute. The Boltzmann distribution has a temperature, right? So, as I heat the air in this room, let's say the average temperature gets higher, the average speed of the molecules gets greater. Okay? So what you do with simulated annealing is basically you're going to allow some uphill moves, actually a lot of uphill moves at the beginning. You start with the temperature turned way up. Okay, uphill moves are fine, almost completely fine. Okay, not penalized much at all. And then after you do that for a while, you lower the temperature a bit, and you lower the temperature a bit, and lower the temperature a bit to try to find a good state. Okay. Now the term annealing is also, that's a term from metallurgy. When you anneal a metal, right? If you take a metal that's red hot from a forge and you quench it by dropping it into some cold water, it basically forms crystalline domains. You kind of crystallize in an ugly sort of way. Okay. If you want to kind of avoid this, as I understand this, one of the tools is, well, you want to reduce the temperature much as slowly as possible. Okay, basically, give the molecules plenty of time to you'd like to make like one solid crystal. You'd like to have your axle of your vehicle or your sword or whatever it is you're making be one solid crystal. That would have the most strength. Okay, and your best chance at getting there is to anneal to lower the temperature slowly. Okay, and it turns out that this is an exact analog, and we're basically using the physical principle here in the context of doing hill climbing optimization. Okay, and after this was invented, like no one laid out circuit boards like by hand, like from then on. That was a turning point in history because you can just do much better with this approach. Okay. While I'm talking about that, let me just show the Boltzmann thing real fast and I'll back up. Okay, the Boltzmann distribution. So the idea of it is, from the point of view of an AI guy, the idea is, so we're often in a situation where we've got multiple options. We have some scores or some utility or goodness numbers that are associated for each one, but that's not a probability distribution. Okay, and what we'd like to have is we'd like to turn that set of items, and we'd like to turn the scores into a probability distribution over the set. And what would we like the properties of that distribution to be? Well, we'd like it to favor the better scores. Yeah, I mean, that makes sense. We'd like to favor the better scores. And then the beauty of the Boltzmann distribution is it has this temperature parameter, which basically says how much it favors the better scores. And when the temperature is high, it doesn't favor them very much at all. And when the temperature is low, it will only go from one state to one with a better score, i.e. hill climbing as we defined it before. So that's at the temperature 0 or close to 0 range. Okay, so this is the probability distribution. As you'll see, it's not super complicated. Basically just uses the exponential function as our friend here, okay, to turn your scores. So these scores are labeled E's here because in physics they're energies, okay? Takes those E's, they could be positive, they could be negative, okay? We divide by the temperature parameter, okay? And you see what we're doing here is an obvious kind of normalization. If we want, when we sum over all the E's, if we want to get to 1, well, this is the obvious way to do it, right? Just divide by that sum to begin with. So when we sum the numerator, we get the same thing in the top and the bottom. It's obviously going to be 1. Okay? And if you look at this, you should be able to see so what happens if the score is really good? Okay, well, then the E is going to be relatively big, right? If the score is good and the temperature is low, that's what gives you the most probability weight on that item. Okay? Whereas if the temperature gets turned up, okay, a bigger score is always going to have a larger probability. But because of the exponential function, what happens when the scores are large, when the temperatures are large, right? Then you'll have exponents that are just slightly different from one another. And it's almost, for practical purposes, you can think of it as a uniform distribution over your set. It isn't really. It will still always favor the better scores, but so little that it's inconsequential. Okay, so remember this because this doesn't go away in modern AI. It's proven to be a very durable and useful trick. Okay, so genetic algorithms. So yeah, we'll see how this connects to Andy's question here, but this is another technique which has proven durable. To a large extent, it looks to me like a simulated annealing, so it's got some randomness in it. But so interestingly enough, so here we go. Physics, and here's the biology optimization. Optimization is a principle that that we use in scientific modeling all over. It's one of the things that, to the human mind, that explains very well certain phenomena. Okay, and genetic algorithms, now we're talking about improving the genetics of a population, right? To survive better. Think of a species in the wild, but just won't think of humans. It's in big picture doesn't matter, but more natural to think of a species in the wild, right? So if their genetics are poor, and if they're getting poorer over time, we might expect that species to do worse and worse. Maybe it's on its way to extinction, and other species might be doing the opposite. Okay, now what's interesting about genetic algorithms, if you think about how genetics works, genetics have two things at play. I mean, one thing is noise, right? In the genetic context, that's called a mutation, right? There are always mutations that occur. No no child of yours probably will have zero mutations. You know, they'll probably have at least some differences that weren't in your DNA, weren't in your partner's DNA. It's just a random, because it's a physical process to go and combine the DNA, and it's subject to what happens in the real world, which is accidents. Okay, so that's one thing that's there. Okay, but we already have that. The interesting part for genetics is that it also does crossover, and that's the idea that yeah, there are two parents. Okay, and we for a particular gene, let's say that one that determines the length of your tibia, you're not going to get the one both from your mom and from dad. It will be one. It will come from one of them unless there's a mutation. It will generally come from one of them, but just one. Okay, so that's crossover, that we take some elements from two complete specifications of a state, in this case, designed for a creature, and we combine them in some way to make one whole. Okay, is that clear? And to me, given with the randomness already in place, that kind of connected a little bit to what
Yeah, I think so.
you were asking. Okay, now it's so it's a cool idea, and its strength, though, is really what's novel about it is not the noise, because we knew about noise before genetic algorithms came around. It's the crossover, and crossover makes sense in some circumstances, and maybe less sense in other senses, in other circumstances. So I'll show you an example where I think it makes pretty good sense. This is not mine. This is somebody else's thing. So here we're evolving vehicles. Okay, now each one of these vehicles, I wish I could stop it. Okay, each one of these vehicles is specified by a bunch of numbers. Radius of the front wheel, the radius of the back wheel, and then a bunch of numbers that determine, you notice from the centroid here, it's just a bunch of radii coming out from that centroid. Those distances give the shape of the vehicle. And then they're just assuming, I think, that is just a uniform homogeneous mass. So that is also the mass distribution on the vehicle. Okay. And what you see here is a genetic, like it's maybe not a classic genetic algorithm, but definitely genetic flavored algorithm at play. Okay. So what's going on is we want these things to go as far as possible. That's why you see the meters over here. Okay. And the way you work when you work with genetic algorithms, unlike the hill climbing, we always have our one favorite state for hill climbing, right? For genetic algorithms, we always have a population of entities. So we start with a population, a bunch of randomly created vehicles in this case. Okay, we run them, and then depending on how well they do, we favor the specifications of the better performers. And those could be mutated, and they could also be crossed over with other good performers. Right? And sometimes that'll be brilliant, and sometimes it'll be a disaster, and sometimes it'll be a crossover. Doesn't matter much. Look at that. Boy, that's a weird one. Yeah. So it's kind of fun to watch these. So the link is in your in the notes, so you can spend more time with it. It's got some controls to it, so you can kind of it's kind of fun when they drop them all down on top of one another. Ooh, that one looks pretty decent. But I'm still worried about those spikes. It would be better to be round on top. It would give you a chance, I would think, to flip back over. Or am I thinking wrong? I'm not sure. See now, yeah, that's what I thought. Okay. All right. So that's genetic algorithms. All right. So distribution. All right. Okay. So now we're going to switch gears and get to what we really want hill climbing for this class, which is continuous hill climbing. Okay. Similar in spirit, but different in the details of the algorithm. Okay, so now we're going to assume that our solutions have floating point numbers in them. Again, and quite often, for neural nets, that's all it is floating point numbers. So a neural net specification at the end of the day has some connection information about the neural nets. We'll talk about that in the next unit. Okay, but everything else is just a list of floating point numbers, which indicates strengths of connections between the neurons and some other things. Well, that's for later. Okay. Okay, so now we have floating point numbers. This whole scheme that I put up with is just nonsense, basically. I mean, because there are so many floating point numbers. Even if we looked in the tiniest region around, let's say it's just the state is just one floating point number. Okay, that can't be a neural net. So there's always going to be more than just one. And often there will be millions and millions. But let's just say we have to optimize one floating point number. How many are in a small region around that floating point number? You know, an incredible number of them. And if there's two floating point numbers, so we're in the plane, or three, so we actually could visualize it as a volume, the situation just gets worse and worse and worse. It starts ridiculous and it gets more ridiculous. Right? So that's not going to work to just like look at everything nearby and see which is the best and go to the best. Okay. But what lets things work is that in many cases, that there's no guarantees of this, but in many cases, the scoring function, okay, which is a function of my floating point numbers, is a smooth and in fact a differentiable function. And if the function is smooth and hopefully in fact differentiable, then we know what? We know that if you just tweak one of the floating point numbers that determines the state, that the scoring function being smooth, it won't have changed very much. Okay? And so this gives us the leverage to say, oh, okay, so if we know that's the case, then let's see what we can do. Let's leverage that to try to get to an algorithm that'll work. Okay? And we do it in a very specific and also still very simple way. All right. Now, before we get into the algorithm, I'd like you all, if you have your computer out, you can go to this link and give this a try. But I don't even know if I'll be so generous as to give you 5 minutes, just so we understand what the problem is. If you can follow along with me, if you don't have your computer up. So this is the app. Okay. The point is, here's my state. It's two floating point numbers. I've got a scoring function. We don't know what that scoring function is, okay, in this case, but, I can go and put some numbers in 2 and 2. That looks good to me. Okay, and you see it says, okay, your goodness is about 5.2. Okay, then I can say, all right, well, what if I raise this up to 3? Oh, no, that was moving down in the wrong direction. Okay, what if I make it 1? Maybe that's better. That actually was better. Okay, well, maybe 0 is even better. It is. Maybe this should be negative. Maybe even more negative. Yeah, it's only doing better and better. 8.4. You tell me when I'm going down in the wrong direction. Oh, I went down in the wrong direction. Okay. All right. So now obviously I can zero in, and even just zeroing in to optimize that one parameter, I can spend all afternoon doing that, right? I mean, it depends on how many digits of precision you want to go to, and how small a change in the scoring function is actually significant. Okay. But let's say I got done. Let's say I spent an hour. Okay, -2 is actually the absolute best. Okay. Now I can go and start playing with this one. 7.8, that's better, isn't it? Oh, 2 was better. Maybe we want to go low with this one too. 3, I think. Did we go up or down? I think we're still going up. I think I'll just stay with integers, okay? But that's not the game here, right? You can go into okay. Let's say I optimize that one now. Okay, am I done? Can I go home and say, yeah, so that's the best I can do, or is there more I should do?
Because we don't know anything about school. Want to try some random stuff.
You could try you can restart, do a random restart. Okay, short of that, just for solutions around these coordinates, should I be confident that this is at least locally as good as I can do? I mean, I optimized both of the numbers. So they're therefore both optimized, right?
You can step back and check adjustments to 1 again.
Yeah, do I need to do that?
I would think so, because
Okay, so like imagine if you're climbing up a hill,
No, no, you don't, sorry.
if you're climbing up a hill, right? And I go and I'm trying to go just along the x-axis and do the absolute best. I don't know where that would be, maybe along this axis, maybe out like here, right? Just along this axis, and then I try to optimize along this axis, and that might be actually might still be about in the same location. So this is actually an example that doesn't prove my point.
Well, you do that hill basically along the old line X right there, so you're gonna have that.
You don't have to go back, it's a circular hill, but, you know. The maximal value on the x-axis is not necessarily aligned with the maximum on the y, right?
Yeah, that's
So-
my point. Even though this example doesn't really, I'm trying to figure out what do I need to do? Is it tilted over more? Would be more obvious.
Yeah, so it's a little.
You can also put in another,
Yeah, I think my intuition is getting
put
me.
in another contour line off the axis, because you know, wherever the top place on the axis doesn't necessarily align on the bottom, you could be 10 feet to the left of it. Never know.
Okay, yeah, I mean, I think that's generally right. That's sorry, the illustration, not helping. Go. All right, but in general, you do have to go back. Yeah, just because you optimize for one, and again, these functions don't just look like one hill necessarily, right? They can have any shape. Where at this point, we're assuming they're smooth, but so what? They're smooth, they can still look like this, right? You know? And it's still smooth. So yeah, in general, just because you optimize Y before, as soon as you touch any other variable, you would need to go back to make sure you're still at an optimum. And in general, you won't. Yeah, and presumably what you would probably find is that after I optimized Y, then I did X. When I go back to Y, I probably don't have to move it as much as I originally did the first time, but I still have to move it, and then I'll still need to move X again too if I'm trying to do the absolute best. Okay. Yeah, bottom line, this is a lot of work for a person to do, and definitely something we would like not to do by hand. So let's look for an algorithm. Yep. Okay. Let's look for an algorithm. Okay. So we got smooth and differentiable scoring functions. That's what we're hoping for. Let me just remind you of some really basic calculus here, because calculus is definitely needed to understand why this algorithm is going to work at all. Why it makes sense, yeah, I mean, I'm not sure I'm providing enough depth to make sure it makes sense, but even to understand what it does, what the actual algorithm is, because it has a derivative. So, okay, all right. So just like to really stay at kind of baby calculus level, I'm gonna kind of purposely not dive deep, and you don't need to dive deep, I don't think, to follow the algorithm, to prove things about the algorithm. That would be another story. Okay, so you remember the power rule, right? So you have x to the power n. Okay, when you take the derivative of that, right? Exponent comes down and then it gets reduced by 1. We got that. Okay, so that's good enough for my slides. Okay, and you remember that's like the simplest case that you learn. Everything else is harder than that. Trig functions are harder. Everything else is harder. But it's a nice, easy one, so good enough for now. And then the second thing, which turns out to be really important for something like a neural net, is a chain rule. Okay, and the chain rule assumes that you have two functions that are composed. That means that this one function, which you're going to be trying to optimize, is actually composed of a function of the input that you're providing. Okay, this happens all the time, and in particular in a neural net, the second layer of the neural net takes inputs from the first layer. So this is natural function composition. So actually you have a very deep nested set of composed functions. Okay, but you remember we have a way to do this in calculus, a little less basic than that one, right? But if we need to evaluate the derivative of two composed functions, you take the derivative of the first one and evaluate it at the second one, evaluate it at your input point. No derivatives here, derivative here. And then you multiply that by the derivative of the inner function evaluated at the end. Okay, so it's ugly enough to give you trouble, maybe, but not that bad. So that should be enough to get you through optimizing neural nets, pretty much. Now, we do need to talk about something that, unless you're a major and a multivariable calculus course, then you would not have seen this at all. But it's a very simple extension. Again, just to understand computationally what you need to do, that's the easy piece to prove things about it. So these are so-called partial derivatives, right? So, right. So let's talk through this. Right? Good old power rule that we had before. Well, actually, something additional, right? If you have a constant times a function, you know that the derivative of a constant times the function is the constant times the derivative of the function. Yeah. Okay. So that's what's being shown here. And the derivative ddx of x is just 1, right? With the power rule. So that means the derivative of that with respect to x is just c. Well, that's pretty easy. Okay. And likewise, if it was cx squared, well, then same story. You kind of take the constant out to the side because that's not going to be affected, right? The derivative of the product is going to be the constant times the derivative of the second piece, and the derivative of the second piece is classic power rule. So the 2 comes down, the 2 becomes a 1 in the exponent, like that. Yeah? Doesn't get easier than that. All right, but in multivariable calculus, now we have multiple variables around at one time, okay? And for something like a neural net, you always have many variables, okay? So if, let's say instead, we have a function of 2 variables. So to get the output, we have to take this constant and multiply by the value of x, and then multiply by y raised to the second power, okay? All right. So the idea in partial derivatives here is that when you take the, so first note that it's not a normal d in the derivative. So the dead giveaway is they use, those are actually Greek deltas instead of d's. So when you have deltas, that tells you, oh, this is meant to be a partial derivative. And when there's a partial derivative, when you're taking a partial derivative, what you do is, and it's very simple, you just pretend that the variable you're taking the derivative with respect to is the only variable. Anything else that you were just saying it was a variable, but for right now, you pretend it's a constant. Okay? So if we take the partial derivative of f, okay, with respect to x, then x is the only thing we're recognizing as a variable. The c and the y squared, we're going to treat like it's a constant. So we just pull it out to the front. Okay, don't touch it. And we take the derivative with respect to x, which again is 1. So that gives us cy squared. That clear? Right? Likewise, we can take the partial derivative with respect to the y. Now, at this moment, we're considering x as a constant. Okay? So cx is now our new constant. I'll leave that alone. Take the derivative with respect to y. The 2 comes down. It becomes a 1. And this is the answer. Easy, right? Now, to be computationally, it's easy. Yeah. Now, we're going to talk about a property of partial derivatives, which, unless you had a real multivariable calculus course, you'll probably have to push the I believe button. But maybe you can get a little feel for why it's true. I'm not sure. We'll, that'll be on you. I'll leave that as an exercise for you. Let me show you what the algorithm is. So now that we have partial derivatives, I can show you what our continuous hill climbing variant looks like. So here it is. So it's called the gradient ascent algorithm. If we need to flip around and we need to talk about costs instead of benefits, then we would be trying to minimize the score instead of maximize. And then you'll hear people talk about gradient descent. And in the context of neural nets, often the cost function is, so the scoring function that's used is a cost. It's your error. Okay, it's an error. We want to minimize that thing. So that's why as soon as we start talking about neural nets, you'll say gradient descent instead of ascent. We want to go the other direction. All right. All right. So the general concept here, as with all derivatives, okay, well, so the derivative of the quality function with respect to each floating point parameter gives us a direction that is uphill, and then we're going to use that information to move uphill. So that's the idea. So at each update step, if Q is our quality number and X is, let's assume we have just one floating point parameter. Okay, and its current value, at the kth step, let's say we've been doing this algorithm for a while, we're at the kth step, its current value is X sub K. Okay, so that would mean I should probably have a K up here too. So what we're going to need to do is we're going to need to take the old value of X sub K and add this thing, which is an eta, that's just taken to be a fixed small number, sometimes called the learning rate. Okay, and we multiply by the partial derivative of Q with respect to X, as we just showed on the last slide. Now, if X is all there was, this wicked partial derivative is the same as the normal total derivative. Okay, and when you only have one variable around. So that's easy. Okay, so that's going to become our algorithm. You maybe get the most you've ever gotten out of calculus here in an applied setting, and we wouldn't be able to optimize in the lens without.
And you're doing that for every parameter.
Yeah, if there are multiple parameters, right now let's just say we have one, but yes. Okay. All right. So again, Greek eta, that's this guy. It's called the learning rate, taken to generally be a small positive number. Okay. Now, you know that derivatives, if I take the derivative of a function at a point, okay, and the function is smooth and differentiable, and differentiable into its derivatives, if you want to be trying to talk like a mathematician, you have a lot to say, okay, then you would know that the derivative at this point shouldn't vary very much if I go a little to the left and right of the point, okay? But after you move some distance away, and sometimes the distance is very small, it can change, and it can even change drastically, right? I mean, think of like we're taking the derivative at of a parabola and stepping across the origin, right? On one side, the derivative is negative, on the other side, it's positive, right? So small changes can sometimes make big differences. Okay, so keep that in mind, and that's the reason why we try to. That's the reason why eta is small. No, I probably need to say more to truly convince you of that. That is the reason. Greek deltas are partial derivatives, okay, and we stop then when the derivative is close to zero. Okay, when the derivative is close to zero, it's going to be the same story that we had with our discrete hill climbing algorithm. We'll see that the x's are not changing very much, right? It's close to zero or literally zero, it won't change at all. Okay, if it's close to zero, it will change but it will change very little. Yeah. So that is the basic algorithm. I have more to say about it, but that's it. Okay. All right. So let's just do some examples to kind of get a feeling for how this works. Okay. So if we say this is my Q function, and see, it's a nice, smooth, looks like a differentiable function of X. Okay. And let's say that this is my current location. Okay. And let's say let's try to follow the algorithm as best we can in a hand wavy kind of way. We have math to do here. Okay, is that derivative positive or negative? It's negative. Okay, so what did the algorithm say? It said to take your old value there and add in eta, which is just some small positive number, times that derivative. Okay, that derivative is negative, and so which way am I climbing, right or left? Left. Okay. Which is good, because I would not be climbing if we're going right, not from this location. So you're going to go like this. And again, once again, when you evaluate the derivative here, it's going to be what? Even more negative. Okay, so we're going to keep moving like this. Now, as we get close to the top, what's going to happen to the derivative? What's the derivative up here at the very peak?
It's going to be zero.
It's going to be zero. So you see that the amount X is changing through passes of this algorithm will eventually reduce. Okay, and probably we'll get tired and say, that's good enough, let's stop.
And Eta does not change as derivative of cosine zero.
Eta does not generally change for this basic
So
algorithm.
you're essentially taking a continuous function and evaluating via discrete stepping function. So we're like if the
I mean, the
ideal
algorithm is,
if the ideal derivative is zero, you're not gonna hit exactly step over.
yes,
And then it's gonna
yeah.
but there's eta is the interval, so you're never gonna hit the actual.
In general, that's correct. Your intuition is right. Okay, I also have, okay, so that's one thing, help with your intuition a little bit. And we can go online, and here is a another, here's an example. This is the function we want to optimize, and the little spike here just shows our current value of x. Okay. And when you click update, it actually just does the gradient algorithm for you. So hopefully you can kind of see what it does. Okay. What's it doing? Looks like it's climbing this peak right here, right? Let's see. And we should see it slow down. And about this point, I don't even see, I'm clicking like mad. I don't see any change. Okay. And you can reload this and start somewhere else. We see, okay, now it's climbing a different foothill. Again, you see, to actually get, if you really, really, really want to get to the main peak, you've got some work to do one way or another. By adding noise, by doing restarts, one way or another. All right. Where are we? Okay, you could also do this by hand. Okay, so if I gave you this function, I'll say this is your quality function. Okay, it looks like that on the right. So it's got a cosine part, but it's also got a parabola added to it. Okay, and you could easily go through and you write code to do this, right? You do it by hand, right? Here's what the derivative is going to be. If you remember that the derivative of cosine is minus sine, you ought to be able to confirm that. Oh yeah, that's just the derivative. Okay, then we can take eta to be 0.1, and then you can set x to be your initial guess. Then this would be the update rule. Set x to be the old value plus 0.1 times this derivative evaluated at the current x. Yeah, it's as easy as that. How long would that take to code? Not very long. Okay. All right. All right. Now, in general, for useful problems, there will be many variables that need to be optimized. Okay, so our scoring function, our quality function Q, will have n parameters here. And yeah, for modern neural nets, I mean, actually, that's one of the things. I think it's almost like a newspaper level thing where they will talk about. I mean, these days, like there'll be 1 trillion parameters in a language model, which is a neural network. So n could be 1 trillion easily. Okay, just vast. But the algorithm, the basic algorithm, okay, you will know by the end of the quarter really, really close to what people are doing. They're doing things slightly more complex than this, but really not so as you. It's an important difference. Okay, well, it isn't important, but very mildly different from what I have on the board right here. It's basically just taking partial derivatives, okay, of quality. Quality often would be, again, and for neural nets, we often make it a cost, right? So the cost is our error, what the performance we would hope what the performance should be versus what it actually is, okay? And we optimize it. The difference for if you want to be cutting edge, the main difference here is that eta actually will not be a constant. They try to put some smarts into the eta, but it's nothing mind-blowing. You'll see when we get to it. Okay. Any questions? Are we good? All right.
When people talk about training LLMs from an optimizer that they're using, are they
Yes. That's what they're talking about. They're talking about a replacement for this. And in software that would go and optimize an LLM or any neural net for that matter, if you look for something, it'll usually be called stochastic gradient descent. That will be exactly this. It's still something that is used. Okay, so this is close enough to the mark that it's still in routine use. But normally, to be honest, these days when I train things, I do something a little more complicated than this, but not much. Okay, I'm over time, so we'll pick it up again. Where are we? 1100 tomorrow, right?